pleasure to have Bob Penna visiting us from Harvard CFA. Bob is a graduate student there working with Ramesh Narayan on his thesis. Before Harvard, he was at the University of Rochester, and he did some research with Eric Blackman while he was there on shearing boxes and dynamos in that case. Since coming to Harvard, he's done most of his work on black holes or on accretion flows onto black holes, and today he's going to tell us about some of that work.
Thanks, Shane. Right, so this is the work I've been doing over the past few years. It all grew out of this larger project to measure black hole spins, and to measure the spin of a black hole, you need a good model for the accretion disk. In the process of studying accretion disk models near black holes, some other interesting physics appeared, so that'll form the basis for this talk. Before I get into it, let me just say a word about black holes. It's a remarkable fact that every black hole in the universe is described by the Kerr metric, this simple equation here. It just has two free parameters, m, the mass of the black hole, and this other parameter, a, which sets how fast the black hole is spinning. And a major motivation was to measure this guy, the spin parameters of astrophysical black holes, as I'll describe in the next couple slides. And as beautiful as the Kerr metric is, it can't be the whole story on black holes. It has a number of problems. It has a famous problem of having a singularity in the center, but there's other ones as well. There's an inner surface called the inner horizon that's unstable, and the event horizon has problems. Hawking showed it doesn't conserve information. So the big hope, I think, for some of this research is that by studying astrophysical black holes, maybe eventually one will get hints about what lies behind the Kerr metric. And before I go any farther, let me say a word about units and size scales. So given a black hole with a certain mass, I'm mostly interested in stellar mass black holes, so say 10 solar masses, and fundamental constants, G and C. By dimensionless analysis, you can form a length scale, gm over c squared, which comes out to be about 15 kilometers. So that's a typical size scale for these problems. Things have sizes of 15 kilometers. And you can form a time scale by dividing again by c, and it comes out to be 50 microseconds. It's a typical time scale that these things are happening on. What I'll do from now on is I'll set g and c equal to 1. So both of these, length and times, just become m. And so this becomes a funny way of measuring things that people in this business use. So you might hear me say something like the event horizon has a radius of 2m. Well, I mean 2 times this. I mean 30 kilometers. Or I'll say something like the simulation ran for 20,000 m. Well, I mean 20,000 times this unit of time. So a little less than a second. And this is the system we're interested in, a galactic X-ray binary. The black hole is here in the center of the accretion disk. It's being orbited by an ordinary star. The star is dumping fluid onto the black hole. It has lots of angular momentum, so instead of plunging radially, it forms a disk. And what we're really interested in for black hole spin measurements is the very inner region of the disk, where it's really hot and X-ray emitted. We zoom in on that region, we find that the disk doesn't go all the way down to the black hole. It's truncated, and this is what's going to let us measure black hole spin. The fluid out here is going around on circular orbits, but at some point, general relativity says that circular orbits become unstable. And so the radius where that happens is called the ISCO, the innermost stable circular orbit. When the fluid reaches the ISCO, it doesn't have circular orbits to continue on, so it just plunges into the black hole very quickly, pretty much radially. So this becomes very low density, it's dark, it's like a hole in the middle of the disk. And the key point for black hole spin is that the radius of the ISCO is a strong function of how fast the black hole is spinning. So if the black hole is spinning rapidly, the ISCO moves in and becomes closer to the horizon. And so if you have a good disk model, then from X-ray observations, you can back out the radius of this ISCO. And you can work out the spin of the black hole. So let me expand on that for just another minute. Here's the actual GR prediction for how the radius of the ISCO, measured in those funny units of m. So this m is 15 kilometers for a 10 solar mass black hole. Here's how the radius of the ISCO varies as I change the spin of the black hole. So this A measures how fast the black hole is spinning, and the way A works is 0 means non-spinning black hole. So this is the Schwarzschild metric non-spinning black hole. ISCO is at 6 times 15 kilometers, or 6m. And then as you spin up the black hole, the ISCO moves inwards. So the inner edge of the disk moves down towards the horizon. And this is normalized so that here at A equals 1, you're at the limit. You can't spin any faster. You're spinning so fast that the event horizon is moving at the speed of light. So that's a limit to how fast you can spin. And negative A mean that the disk and black hole are rotating in the opposite sense. So between negative 1 and 1, this ISCO changes from being at a radius of 9 to 1. So there's a big fat factor of 9 there. That's the kind of thing you can hope to go out and measure.
Oh, Magnus, the Schwarzschild radius is at 2 in these units.
The Schwarzschild radius is at 2 in these units for a non-spinning black hole.
And at which point does this thing go inside the Ergos field?
Yeah, at about spin of 0.6, this goes inside. This goes inside the ergosphere about 0.6 or 0.7. Yeah, somewhere around there. I forget the exact number. And yeah, all the radii are moving. I just showed one. But the event horizon for a non-spinning black hole would be at 2m. That's actually also shrinking down to 1. So to actually measure the spin, you need a disk model. And the model that has been delivering results now for some time is the Novikov and Thorne model. It's the standard Kerr-Sinyaev thin accretion disk model, but with relativity. And here, just to give you a sense, I'm showing some Novikov and Thorne solutions. So these are luminosity on the y-axis versus radius in the disk. And there's 4 different models here. These are 4 different spins of the black hole. The Novikov-Thorne model assumes as a boundary condition that this luminosity goes to 0 right at the ISCO. Like we saw in the picture, that there's a dark hole in the middle of the accretion disk. So here, the cyan line is this non-spinning black hole. The luminosity is going to 0 at 6m. That's where the ISCO was on the previous plot. As I increase the spin of the black hole, the inner edge of the disk, where the luminosity marches inwards. Yeah? And the whole disk just becomes brighter. And so if you know the mass of the black hole and its distance and the inclination of the disk using other means, then from an observation of the X-ray luminosity and spectrum, you can back out the spin of the black hole by fitting one of these Novikov and Thorne models. And this has been going on now for some years, and it's delivering results. So here are 8 galactic X-ray binaries with harboring black holes, and here's the spin of the black holes that have been inferred using this method. And this is kind of interesting. They range from almost 0, almost no spin, to very rapid. There's no negative spins, which says something maybe about how these things form. And I think it's interesting that there's spins very close to the limit. There are mathematicians studying the stability of the Kerr metric and thinking that maybe very rapidly spinning black holes become unstable. But if nature is forming them, they can't be too unstable. So those spin estimates rely on having a good model for the accretion disk. And so the remainder of this talk is about testing our understanding of accretion theory. And there's 2 assumptions really that I'm going to talk about today. So one I already talked about. There was this assumption that the disk has a sharp inner edge, and that we can identify that sharp inner edge with the ISCO. This has been questioned because these old models from the 70s didn't have magnetic fields and turbulence, and everything would be more complicated in real life. So we're going to do simulations and test that assumption. And the other assumption I haven't really touched on yet. The disk is very complicated. Angular momentum is removed using turbulence stresses and magnetic fields, all very messy. So in the standard disk models, all that complication is just folded into this alpha parameter, and then people guess values for what alpha is and how alpha behaves. With simulations, we don't need to assume any sort of alpha parameterization. We can just generate turbulence and magnetic fields self-consistently, we can go in and empirically measure alpha, and we can just see if it's similar to what people have been assuming. So those are the two assumptions I'll talk about. We'll start with the first one. So let me say a few words about the simulations, what we're using here. So I'm using a conservative GRMHD code HARM. And the GRMHD has the GR is, of course, general relativity, and the MHD, magnetohydrodynamics. And this HARM lets us solve GRMHD in 3 dimensions. And we work in the fixed Kerr metric. So it's a spinning black hole, and we can change the spin parameter. That's one of our free knobs. But we don't evolve the metric at all, and the disk has no self-gravity. There's no radiation. That would just get too expensive. So to make thin accretion disks, we have to do something to let it cool radiatively. So we add this sort of ad hoc, but also physically motivated cooling term into the energy equation, just to keep things like a thin disk. And here's how this works. It's very simple. You specify a target entropy for the gas. And whenever the gas gets hotter than your target entropy, you just start cooling it back down. And you cool it back down on some cooling time scale, which is related to the orbital period. We think this is a good description of what happens in a time average sense when things are optically thick and cooling efficiently. And this parameter, this target entropy, adds another free parameter we can play with. And setting it low and making a cool disk will make thin disks. And making it high will make thick disks. So it lets us make a family of models with different disk thicknesses. So we basically have 2 parameters I'll talk about. How fast is the black hole spinning, and how thick is the accretion disk.
Is that parameter independent of radius?
Yeah, I just set it to be a constant dependent of radius.
Can you say that similarly is that the accretion rate is one of your 3 parameters rather than the disk thickness? Is it directly related that way? Or not?
Yeah, because there's no radiation and there's no self-gravity, the density is just normalized away so that density equals 1 at some radius. So the accretion rate, its overall scale, is the normalization is really arbitrary. So the units of MDOT are pretty meaningless. The thing that we can measure and is a good observable is H over R. So you can have a thin disk with H over R of 0.1, and then you can look at models that have radiation, and you can say, okay, that corresponds to accreting at about 30% Eddington. And then you can look at another, by changing this, I can make a very thick disk. And then those are the ones we call sort of Eddington limited accretion flows. Yeah. But I don't really think, so I'm just saying I don't really think of MDOT is equivalent in some sense, yeah. But in this indirect roundabout way, yeah.
If you set a particular H over R, can we then say, okay, that corresponds to this fraction of Eddington?
Yeah, what I do is I set a particular H over R, and then I'll look at a model that has radiation. The ones I like are these slim disk solutions. Yeah, and those are inferior in the sense that they're alpha disks, but I can match my H over R to the H over R of one of those, and then I can see the MDOT of that model, and then that's how I get some handle on what accretion rates these are at. But without radiation and self-gravity, that's kind of the best you can do. Yeah. So I'll talk about H over R as the free parameter, but you can think of it in your mind as MDOT. It just takes a few steps to convert. Okay, and so the code, what is the code actually doing? It's solving conservation laws. So the fluid has a stress energy tensor. There's a fluid with a 4-velocity u mu. There's a magnetic field b mu. And the fluid has a rest mass density, an internal energy, a pressure, and then the magnetic field carries internal energy and pressure, magnetic. We connect the internal energy and pressure of the gas with an equation of state, which is an ideal gas. This gamma can be 4/3 or 5/3. Having done both, I can say it doesn't really change any of the results. And then the code just solves conservation of rest mass and conservation of energy and angular momentum. And this thing on the right-hand side is that cooling term that I described in the previous slide. And I'll just show you a movie to give you sort of a mental picture for what's going on. This is an example of a thin accretion disk. H over R here is 0.05, and the black hole is not spinning. The gas starts out in a torus out of 20 gravitational radii. That torus is going to sit there the whole simulation and just act as a reservoir of material to keep resupplying the accretion disk as gas is accreted out of the black hole. And that initial torus is threaded with colloidal magnetic fields. They start out really weak so that the magnetic pressure is just 1% of the gas pressure. The resolution of this example is low. The more recent ones have 4 times higher resolution. But in this example, there's 256 cells in radius. There's 64 cells in theta. The theta grid is deformed so that most of that resolution is in the midplane, in the disk, the region we're really interested in. And this example has 32 cells in the phi direction, in azimuth. And it's run for 30,000 M, where I'll remind you that funny unit of M in real life would be 50 microseconds for a stellar mass black hole. If you're interested in supermassive black holes, you just multiply everything by 1 million or so. So here's what I just described sort of looks like. 2 panels. This is rest mass density on a log scale. This is magnetic energy density. So here's the black hole, and this is a cross-section in the colloidal plane through this torus. So this torus, wraps around the black hole. The code can't handle a vacuum, so we put it in a thin atmosphere everywhere else. So this stuff here is this fluff, this atmosphere. That's going to fall in the black hole once I click play, or at early times, let's say. It's not going to affect things at the end of the day. This torus is the key. The torus is in hydrostatic equilibrium, so it would just rotate happily forever. But we don't let it do that. We thread it with these loops of magnetic field. Once you've done that, it's unstable to the magnetorotational instability. So these magnetic field lengths get sheared out and become unstable. That generates turbulence. Turbulence transports angular momentum outwards. That lets the torus accrete inwards, and you form a disk in this region, and that disk is what we study.
There's no net flux coming in and out of this? It's just
No. It's all here. No net flux in and out of the disk. Yeah. Okay, so I'll click play. And this, I think, is more fun to watch. Initially, you see the symmetries getting broken, and I guess I'd call that the linear phase of the MRI, and now it's becoming turbulent as you enter the nonlinear phase of the MRI. The turbulence starts to transport angular momentum outwards, so stuff can accrete inwards, and you can see gas is starting to leak off the torus. Still early though. Okay, gas is now extending pretty much down to the black hole. It's not going to visually change very much. The initial torus was out here, so all of this gas is what I call the accretion disk. And so I'm going to focus my investigations on this gas here, this disk. The magnetic structure is interesting. It's turbulent near the midplane. You can see the turbulent eddies. And above and below the midplane, it's become highly magnetized because magnetic fields are buoyant and they rise out of the disk. And this region becomes laminar. So this is what I'd call the corona up here, and this is what I'd call the turbulent disk. So the first thing you want to ask is, does the simulation reach some steady state solution? And so one way you can sort of answer that question is you can look at conserved quantities. So here what I'm doing, I sit at the event horizon, I watch the fluid go by me, and I measure its angular momentum. So angular momentum is a function of time sitting at the horizon. And sure, early on there's some transience as things are settling down, and then it's still fluctuating because the flow is turbulent, but it settles down to some sort of mean value. So I would call this the steady state period of the flow, and whenever I show you results, there'll be time averages over the steady state period of the flow. there's already an interesting piece of information here. This dashed line is the prediction of the Novikov-Thorne standard thin accretion disk model. It's a little lower. That means the stresses have been a little more efficiently than we had thought at removing angular momentum from the gas. Okay, that's at the horizon.
So,
Yeah.
maybe you could say that, but is that the same as the ISCO? The angular momentum that is in the Novikov-Thorne model?
Yeah, in the Novikov-Thorne model, this is just angular momentum at the ISCO.
It is ISCO.
They assume, yeah, at the ISCO, you just plunge conserving angular momentum.
And simulation, you
When
also
you didn't
measure
check
ISCO.
though at the ISCO, you checked at the horizon.
Yeah, I'm sitting at the horizon here.
So
And-
is that difference?
Yeah, the difference is mostly, yeah, the two effects are comparable. There's two effects. One is that in the simulations, there's some stresses inside the ISCO, unlike Novikov-Thorne, which keep removing angular momentum. And the simulation is slightly below Novikov-Thorne at the ISCO, but it's actually the first effect that's stronger.
The Maxwell stress, that is?
I'm sorry.
The Maxwell stress, that is, inside the ISCO?
Yeah, exactly. Okay, so that was sitting at the ISCO. All the angular velocities are largest in the inner parts. Everything's moving really fast. So the time scales are short in the inner parts, and things settle down quickly. In the outer regions, everything's happening slower, and it takes longer to reach this steady state. So another interesting plot to look at is this one. This is accretion rate versus radius. And in steady state, conservation of rest mass would tell you that this thing should just be razor flat, because rest mass is conserved. And it's really nice and razor flat, but only out to about 10 gravitational radii. This is that same non-spinning black hole. The ISCO's here at 6. Maybe you can believe results out to 15, but then it really starts to deviate. So in addition to time averaging over steady state data, I'm also really going to only trust the innermost radii of the simulation. The initial torus was here. So I don't really look at the stuff that's in the initial torus. So those are the sort of range of radii, I'll believe, for thin accretion disks. Let me just make one comment. Thick accretion disks, everything's happening even faster. All the velocities are larger. There's larger radial velocities. So you can get convergence not up to 10, but maybe up to 100 gravitational radii. You had a question?
Yeah, in order to be in steady state, you have to keep feeding the torus with more stuff, or is the accretion out of the torus low enough that it doesn't matter?
Yeah, accretion out of the torus is low enough that it doesn't matter.
Is this measured on a cylinder or on a shell, on a sphere? Like the radius, the
Yeah.
radius is
Yeah, it's kind of a neat point. Yeah, it's measured on a sphere.
on a sphere.
Yeah, for a thin accretion disk at least, I don't think it really matters. Okay, so we basically had two knobs that I was going to talk about today at least. Spin of the black hole and thickness of the disk. So, and the problem we're interested in right now is this assumption of a sharp inner edge at the ISCO a good assumption? So here's something. Let's keep the spin of the black hole fixed, a non-spinning black hole, and just look at disks as we increase their thickness. So here you're looking at cross-sections, colloidal plane, 4 different simulations. All of them have non-spinning black holes. All I'm doing is making thicker and thicker accretion disks. And it's kind of interesting. The dashed line is the ISCO. Thin, thicker, even thicker, and thickest. The thinnest guy has this, the density increases and then drops sharply at the ISCO. All of the intuition from Novikov and Thorne is working quite well. There's a low density region inside the ISCO.
So are we looking at a logarithmic density map here?
Yeah, this is log. Some log scale, yeah. The point is that as you increase the thickness of the disk, that sharp drop in density at the ISCO becomes less severe. And then if you go really thick, the density actually just increases monotonically all the way down to the event horizon. It just doesn't care about the ISCO. And so if you're measuring black hole spin, you better not use observations of these sorts of systems, because there's nothing going on at the ISCO for you to measure. You got to stick to thin accretionists. And if you try to estimate what that means, this simulation corresponds to an accretion flow at about 40% Eddington, we think. So the thicker guys are above 40% Eddington. When people measure black hole spin, they're very smart about it. They only use data. So they only use data if the source was emitting at below 30% Eddington. They only look at really thin accretion disks.
Some people are very smart.
Some people are very smart. Shane Davis is in his lab.
Well, I gotta confess, that's not entirely.
Not always, there are exceptions. Okay, well, the point is that these galactic X-ray binaries.
Jeff McClintock was smart.
Well, yeah, the point is that galactic X-ray binaries go through different states. Sometimes they're really bright and they're up at Eddington. They stay that way for a while. And then they go down and they're very dim. And these things have been observed for decades, and they stay in these states for weeks or months. So people, when they measure black hole spin, they just pick out the source when it was in the low luminosity, thin disk states. The transition between these two qualitatively different sort of phases, where you have a density drop at the ISCO and just a monotonic increase across the ISCO, happens at an H/R of about 0.1. I've looked at this a little analytically, and it seems that the key criterion is for whether you're in this state, density drop at ISCO, or in this state, no density drop at ISCO, is whether or not H/R is less than or greater than this viscosity parameter alpha at the ISCO, which is kind of neat. This criterion, as a definition of thinness, shows up all over accretion disk theory. It determines, for example, whether or not a tilted disk will align. Tilted accretion disks align with the spin of a black hole only if they're thin in this sense. I think that's all I want to say. I'm going to keep going.
So what do you do to adjust the thickness? You change the entropy to tolerance, or?
Yeah, so that target entropy parameter, you can dial that up and down. And I set the target entropy in that cooling function to be the entropy of the initial torus. So I'll start with a really fat, hot initial torus, and I'll get out a thick accretion disk. Yeah. So that was kind of qualitative. Now I'm making that a little more quantitative. Showed this earlier, luminosity versus radius for Novikov and Thorne alpha disk models. Dashed lines, Novikov and Thorne, there's 4 of them for 4 different black hole spins. Black lines are the simulation data. At large radii, things agree quite nicely. Novikov and Thorne says luminosity goes to 0 exactly at the ISCO. Simulations say, well, there's not much luminosity inside the ISCO, but there is some. So you get these deviations from Novikov and Thorne. Then you can try to estimate how much error this introduces in the black hole spin measurements, which assume the Novikov and Thorne model. So what we did is we took the simulation data and created mock X-ray spectra. And we gave it to Kerr, which is the program that they use. I mean, it's the software they use to measure black hole spins. And we said, Kerr, here's some data I generated using my simulation. I know what the spin of the black hole is. See if you can tell me what it is. And using your Novikov and Thorne based model. And it does pretty well. So depending on inclination, you give the Novikov and Thorne based methods GRMHD simulation for spin 0, and it spits back things like 0.1. So it's pretty close. And you give it 0.98, and it's really close, 0.985. So these black hole spin estimate errors are small. They're smaller than the observational errors for now. So for now, Novikov and Thorne and this assumption that you have a sharp inner edge at the ISCO all seems pretty good.
So does this depend at all on the magnetic topology that you initialize?
Yeah, so that's like the other free parameter in these models that I sort of left out of this discussion to keep things short. Sure. There's basically 2 limits, weakly magnetized and strongly magnetized. I've made every effort to make things as weakly magnetized as possible, putting in the smallest seed fields with the least net flux, assuming that in real life, all of the magnetic fields are generated sort of in situ by dynamo from small-scale stuff building up. There's an opposite limit where you just start out with as much magnetic flux and field as you want as possible, and you get these highly magnetized flows, and those behave very differently. So we can have a discussion about which is more appropriate to these systems, but I think this is... Okay, so that was part 1 of the talk. This is the inner edge really at the ISCO. And part 2 is the whole alpha viscosity thing. So let me say a few slides about where alpha viscosity comes from. The problem that they had in the 70s was to figure out what's transporting angular momentum outwards. And they kind of knew that it was turbulence and it was magnetic fields, but those were complicated things, so they folded them into an alpha viscosity parameter and then just start guessing values for that parameter. The simulations, you don't have to assume anything about alpha. You just run them, and then using the magnetorotational stability, you get turbulence. So this is the velocity field in my simulations. Here's a snapshot, and here's a time average, which sort of smooths out the eddies. This is the same one I showed you the movie of. Non-spinning black hole. You can see this beautiful turbulent disk, the churning eddies, and then above it, laminar. And inside the ISCO, it's also laminar. And what's going on there is the magnetic fields rise out of the disk buoyantly, things become highly magnetized. The MRI, the instability, requires weakly magnetized flow. So the MRI shuts off here, and inside the ISCO, the plunging fluid stretches the field, that shuts off the MRI. So these regions become laminar, and the disk is turbulent. So that's what the velocity field looks like.
How many scale heads up with curiosity is the laminar part?
About 3. Is a good number. And I have a nice plot where I actually put a contour of beta equals 1, and beta equals 1 is right here. It's really that, you can really see the MRI just shutting off. And this is what the magnetic field looks like in the same picture as before. So the red lines are the field lines, and in these small scales, it looks like a split monopole with sort of fields coming out here and going in the bottom. And if I zoom out on large scales, you'd see this sort of closes off and forms a dipole. And again, you see turbulent, bubbly motions in the disk, and then smooth magnetic field in this high, bright corona. So that's all very complicated. So now I want to show you how these sorts of things lead one to introduce an alpha, and how we measure alpha from that data that I just showed you. I'm going to just keep everything Newtonian for simplicity, but make all this relativistic and do it all in GR. This guy is angular momentum flux, and that's the thing. That's the puzzle. What's transporting angular momentum? And so this is the stuff transported by the fluid. You have density times velocity times r, so that looks like mvr. That looks like an angular momentum. And you multiply by radial velocity to get a flux. And then you have this other term, b5vr, because magnetic fields can also transport angular momentum. We have this mental picture that there's a mean flow of fluid and turbulent fluctuations on top of it. And somehow the turbulent fluctuations transport angular momentum outwards. So to make that intuition precise, it's really illuminating. If you take each of these fields, the velocity and the magnetic field, and you split it into a mean and a fluctuating part. So the mean is just defined by phi averaging the field. If you do that, if you split the velocity and magnetic field like that, then this F splits into 4 terms. They each have a really nice physical interpretation. You have product of mean velocities. So this is the angular momentum carried by the gas as it accretes onto the black hole, just the mean flow going onto the black hole. Then you have mean magnetic fields. I've replaced the B with a VA for Elfing velocity. So mean magnetic stresses, they transport angular momentum around. And then you have products of fluctuations, the turbulence. Turbulent velocities, turbulent magnetic fields. These are what we need to transport our angular momentum outwards so that the gas can accrete inwards. And if we didn't know what these were, what they did, what Shakur and Sunyaev did, is they said, we don't really know what these are, we don't know turbulent magnetic fields, so we'll just set them equal to alpha. Just call those alpha. And to make things dimensionless, divide out by sound speed squared. Now alpha is dimensionless. And then start guessing values. So people had some intuition that alpha should be about 0.1, and there were some observational suggestions that maybe alpha is about 0.1. The simulations generate each of these terms, so I can just go compute them. I can just divide by this from the simulation. You just measure alpha and see if it has the value you expected. Also, not in the earliest papers, they said, Alpha will probably be a function of radius, but we don't know how, so we'll just say it's a constant with radius. Well, we can just measure how does it vary with radius, and that's interesting as well. This is very non-relativistic. I won't go through the whole relativistic version, but it's just interesting to note you can't add and subtract velocities so easily in relativity. They don't add the same way. The hint, if you wanted to figure out what to do, is that these three terms that we set equal to alpha are the three terms that don't vanish in the fluid frame. Because if you go to the mean fluid frame, this guy's 0. If you're sitting with a fluid, you see no fluid velocity. And so the way you define alpha in relativity is this thing is a tensor, and you measure its R phi components in the fluid frame. And there's a way of doing boosts relativistically. So it becomes the hats indicate fluid frame. It becomes the fluid frame R phi component of F divided by pressure. So let it be, just suffice to say, you can define this in GR and go compute it. I mean, I glossed over some other things. I want to just mention one because I kind of like it. That whole splitting of fields into mean plus turbulent has this effect. If I split these fields into mean plus turbulent, then the average of the product of the field is the product of the averages plus correlated turbulent fluctuations. In a laminar flow, there's no turbulence, there's no fluctuations, this is 0. So the order that you multiply and take averages doesn't matter. People have published incorrect results because they were really familiar with how physics worked in a laminar flow, and then when things were turbulent in their data, they didn't pay attention to the order they were multiplying and averaging things, and so they were getting wrong. So I've spent a lot of time and had fun thinking about how to do these in the right order, and I think it's kind of neat. It reminds me of, in quantum mechanics, there's operator ordering ambiguities. You can have one set of classical equations. When you go to quantum, things don't commute, and so you have to pay attention to the order that you operate, the order that you multiply things. And something similar happens when you go from laminar to turbulent. And I just think, and there's been some neat issues there. Anyways, getting back to this subject, yeah, we can just go measure alpha. So here's 4 different simulations. These two have a non-spinning black hole. This guy's a thin accretion disk. This guy's thick. Same, 2 different thicknesses, but with spinning black hole. And you just go to the data that we have, and you measure alpha, and it's kind of a mess. So it varies with radius in this sort of way. It's 0.1 usually about near the ISCO, but then it starts to decline, and inside the ISCO it has this shape. Confronted with this sort of mess, there have been some that have said, just got to kind of give up on alpha disk models, and everyone should just learn how to do these simulations when they need disk models. It's kind of silly. Kerr is extremely popular paper. Hundreds of papers use it every year. We'd like some understanding of where this shape comes from. So that's what I'm going to show you in the second part of the talk. We're going to try to understand the shape of these curves.
Does it vary with height?
I'm sorry?
Does it vary with height?
These are all going to, all of these I've averaged over theta. It does vary with height. It's pretty much uniform throughout that turbulent, bubbly disk region, but in the corona it's very different. Here I'm really just going to focus on in the turbulent, bubbly disk region.
And are you going to show us the various components?
Various components of alpha? Well, I'm happy to talk about it after, but in these slides, we're just going to look at this, R phi alpha averaged over height.
Cool.
Yeah. Okay, so to build a model for where this shape comes from, we're going to use a little intuition to make it easier on ourselves. I showed you in some pictures that outside the ISCO, which for this guy is here. Sorry, this scale is 0 to 20, and this one's 0 to 200. But here it's 6 where the ISCO is. Outside the ISCO, I showed you things were turbulent, and inside things were laminar. So it's reasonable to suppose that out here, the stresses are mainly coming from turbulence. And in here, they're mainly coming from mean magnetic fields. So those are 2 different kinds of physics, and we're going to build a 2-component model. One that describes the turbulent stresses and one that describes the mean fields, and they'll work in the 2 different regions. So first, let's think about how this curve varies outside the ISCO in the turbulent region. See if we can understand why it varies. A big hint comes from this paper, Pasachan solved this 2008. Here's what this data is. Here's what they did. They did shearing box experiments. So you just have a box of fluid, you put a magnetic field in it, it shears, MRI, a lot of resolution, you can study the MRI. They did these experiments over and over, lots of shearing box simulations. Each data point is a shearing box simulation. Everything they kept the same, only thing they varied was the shear rate, Q. That's the x-axis. Q is how the angular velocity drops off with radius. So here at 3/2, you have a Keplerian flow. Here at 0, you have rigid body rotation. Negative shear parameter, you have your angular velocity actually increasing outwards away from the black hole. And the MRI is stable. So the alpha, basically, which is the y-axis, is 0, and then it increases up to whatever value has the Keplerian flow. Their data is really noisy, so they can't really tell you how alpha varies with shear rate, but alpha scales with shear rate to some power. They don't really know what power because of the noise. They say n is between 2 and 8. Not very good. But
Why is this so noisy?
well, these were very low resolution for one thing. I think their boxes were 32 grid cells in one direction and 128 and 32 in the other. I think it was just resolution. Yeah. So varies with. Now that wouldn't be very interesting for a Keplerian disk because in a thin Keplerian accretion disk, Q equals 3/2. Omega goes as r to 1/3. So alpha going as 3/2 to the n wouldn't give you any interesting. Still just be a constant. What is interesting is that in relativity, if you compute Q more carefully, there's these relativistic corrections. So this guy gamma is the Lorentz factor of the gas, and this guy curly A is a frame dragging effect that you get when the black hole's spinning and dragging space-time around. These two things, gamma squared curly, those go to 1 at large radii. So you're back to your Newtonian, Keplerian 3/2 if you like. But at small radii, those guys are varying with radius. Here's what they look like for a bunch of different disk models. Dashed black is the simplest. That's just analytical circular geodesics in the Kerr metric. Q, with radius, it goes out to 3/2 as you get Newtonian gravity at large radii, but then it varies with radius because of these relativistic effects. And alpha disk models, like slim disks, is one class of alpha disk models. Those guys basically are on circular geodesics, and then inside the ISCO, when you start plunging, things go a little crazy. And GRMHD simulations look like that too. So here's the point. Q, because of relativistic effects, varies with radius. And not by much. It goes from 2 at the ISCO to 3/2. So it only changes by 50%. But alpha goes as Q to some large power. So by the time you raise a 50% variation to some large power, you can get a radially varying alpha. And so let me go back to the plot I showed you before, alpha versus radius. The gray dots are my GRMHD simulation data. And here I fit a model. Here's the model. Alpha goes as Q, and I just picked the value that seemed to work the best, Q to the 6. Yeah, so shear rate normalized by 3/2, 0.025 to the 6. So this number and this number, just pick to fit the data, and those will change as better simulations become available. It's going to asymptote at large radii at alpha equals 0.025. So I think this seems to explain the shape of alpha out in the turbulent regions. Inside, this model for why alpha is large turns over, and so we need a different model to explain that hump. But we kind of expected that, because this is turbulent, and that's mean field stresses. It's two different kinds of physics. So that's piece 1. And piece 2, I'm not going to go through it in gory detail, but if you just take a simple model for gas falling into a black hole in the equatorial plane in a smooth way and stretching a magnetic field from the ISCO, just stretching the field out, and you just measure how the plunging fluid stretches the field, and then you take mean BR times mean B phi, you get curves for stress that look like this green curve. So that fits alpha versus r inside the ISCO. The point is that I think we understand where this variation is coming from. It's just coming from the fact of how the metric stretches a plunging fluid and how the fluid stretches the field lines out. And if you,
That is your measured BRB5.
this is a BRB5, no, not from the GRMHD simulation, but from
You
a
have
sim-
that in your simulation. Why wouldn't you use the measured value?
Yeah, so it's a little subtle how to time average it because of, yeah, you could, one, because you have, yeah, the one subtlety with the simulation is that there's, and it doesn't come up in this talk at all, but there's this dynamo that I mentioned earlier today. So BR is flipping. And so if you calculate a naive time average of BR in the simulation, you actually get 0 because of its flipping. But there's still a mean field. It's just that every 30 orbits, it's a little subtle to calculate because of the dynamo. So this is a model without any of those subtleties that also seems to fit the data.
But it is flipping on the time scale that's longer compared with. the
Yeah, so if you
qualifier.
averaged over less than a dynamo oscillation, you'd get a mean BR and a mean V5 in the simulation that you could plot here and fit the same result. And yeah, I don't have it here, but I've done that, and it agrees with this dash green here.
But it is the case that most of the stress in that iteration is the mean VR.
Yeah. And actually, that should have just, I should have just said that too. Yeah, I've done it. It's not here, but it looks the same. Yeah.
Is it the inflow? Is that like something like Gammy's inflow?
It's
model?
exactly Gammy's inflow model. Yeah, so you know that. And yeah. The reason I didn't show simulation data on this plot is because I wanted to convince you that you don't need to know anything about, you don't need to run your own GRMHD simulations, and you can reproduce this with totally independent models.
And does your exponent there
Yeah,
depend on H over R or on the entropy?
It's, I mean, it's hard to pin it down too much because of just how noisy the simulation data is. So I'm not really sure. I can't really say.
I'm just a little confused because you said about the blue outer curve.
Yeah.
You said that that was most found in small radii where GR is most important for transacting, but you're using it in larger radii.
Well, larger radii meaning only a couple comments. So 20M. You'll still see fringe rating effects. But this particular one that I'm showing you is a non-spinning black hole. All of this radial variation is coming from that factor of Lorentz factor squared. So, I mean, in this particular example, that curly A is not even here. Yeah, but in the spinning black holes, it would be, and change this shape a little bit. And by 20M, it would start to become 1 because the fringe rating doesn't really matter much beyond that.
So if you extended your plot to much larger radii,
Yeah, this you'd expect the asymptote to a constant. It's hard to see that in our simulations because of just, it takes so long to converge. Yeah. So yeah, if you add these two curves together, you get the red line, which kind of fits all the data. I've chosen my favorite simulation here. If you look at the other ones, it doesn't always look so beautiful and perfect, but I think we've taken what was a mess that we didn't understand and brought some sort of organization to it. You can, if you don't care at all about GRMHD simulations, you can take the red curve as just an alpha viscosity, alpha of R prescription, and you can take your favorite alpha disk models, and everywhere you see an alpha, you can just put in that red curve as alpha of R, and it changes your alpha disk models, but just not that much. So here I show before and afters. This is radial velocity versus R and flux versus radius. The dashed line is an alpha disk with constant alpha, and the solid is an alpha disk with my new radially varying alpha prescription. You get small changes in the radial velocity in the inner regions, and at the Eddington limit, small changes in the flux. These are small effects that, with the current data on black hole spin measurements, for example, which are really sensitive observations, are below the observational errors. but it gives you a sense of the changes you would see if you. And it's actually, the alpha of R viscosity prescription might have looked like a huge mess. So I want to give you a practical formula. The radially varying alpha, even though it's kind of interesting inside the ISCO, really only matters out here outside the ISCO, because inside the ISCO, things are pretty much geodesic. They just follow, they're pretty much just in free fall. So stresses don't matter. The disk doesn't care about alpha. The disk really cares about what the value of alpha is outside the ISCO. The discrepancies between the two models are largest there. And outside the ISCO, that red curve, the alpha of R prescription, simplifies to this nice analytical formula, at least for a thin disk. And this thing looks messy, but it's really not. It's actually kind of beautiful. It's just Q of R, the shear rate, for circular geodesics in the Kerr metric. And so if you take this as your alpha of R prescription, you get this red curve, which fits the data out here really well. So this is something you could compute as a homework exercise in a GR class. And then raising it to the 6, and that's just what fits the data. And it's also another neat spin-off of this project. People have done shearing boxes in Newtonian and relativity, and then we've done these relativistic calculations. The relativistic alphas were always coming out to be larger, and we didn't really know why, 10 times larger. And I think it's at least partly because the relativistic community is doing all our simulations here, and the Newtonian shearing box community is doing all their simulations out here. So there's a factor of 6. I think it explains part of the discrepancy. And then I'm kind of out of time, but there's all these miraculous scaling laws that we don't understand where they come from whenever a fluid becomes turbulent. They're seen in shearing box simulations. They're also seen in the global simulation. For example, like you multiply alpha times the ratio of gas magnetic pressure, and no matter what you do to the initial conditions, it just always comes out to be 0.5, and it's just a mystery why. Such a simple formula should have a simple explanation. So this is one of the things that I find neat about working on turbulence, is that there's these mysterious universal formula that we don't understand. To me, they look kind of like being in the 1800s and finding the like Charles law and Boyle's law for the first time, being like, why the heck should P times V be constant all the time? Should be some simple reason. Wrong direction. So that's the whole talk, and this is a summary. Black holes they're all described by the Kerr metric, and that just has 2 free parameters. We set out to kind of measure this one, A, black hole spin. Big assumption was that the inner edge of the disk is at the ISCO. Also this alpha viscosity prescription. You can do simulations and then just go look and just see if that's what happens. And first assumption's okay as long as you're thin, as long as H over R is less than about 0.1 at the ISCO. And you find that alpha actually varies with radius, but we kind of have a model that sort of explains what's going on. So that's the whole talk. Thanks.
We have time for questions. Linda.
So now that you have a better idea of what's going on in big disks, can you look at galactic black holes and measure their spins and not have to be careful that you're less than 30% density?
Yeah, that's the hope that we can do that. Here's what people find. So I just like this plot. How do we draw this? So these galactic black holes go through different states where their luminosity is changing over the years. Some of them have been observed for decades. And you go and you try to measure the spin using data when it's in different states. So using the Novikov Thorne model, people went and measured spin, and they found whenever the luminosity was below 30% Eddington, even observations decades apart always came out with the same estimate. So that's why they cut it off and they said, we're just not going to look at data above 30% Eddington. When you do that, this is generically the sort of picture you find. So they said, all right, and this is true really. Only when the disk is thin does this whole method make any sense? And sure enough, the data, separated by decades of real life, gives you a consistent spin estimate. So you could hope that maybe when the disk is bright and near Eddington and much above 30%, maybe instead of fitting Novikov-Thorne, you just go fit a simulation to it, or a model inspired by simulations. Yeah, that's something we've worked on, and things improve. They don't drop as much, but right now we're not all the way there. Yeah, there's still some other piece of physics it seems like we're missing.
So I can understand how often you have this strong shear rate dependence, and yet always be 2 beta to -1.
Why can alpha be 2? With this, I mean, it's sort of magical, but beta adjusts itself in the
Beta
opposite
itself
way.
also has this.
Yeah,
shear
beta
rate.
must also adjust, have the inverse dependence ratio. I'll be around tomorrow and Wednesday, so I'm in the visitor office. You can walk if you want to.
Okay, well, so we're gonna, as Bob just said, he's gonna be around tomorrow and Wednesday, and we'll be taking around tonight. So let me know if you want to join us, and we'll ask more questions. Thank you.